Yes, welcome everyone to the first session of this conference on AR/VR sound perception. I'm really happy to chair this session with four really interesting papers. So the presentations are about 25 minutes each, and I hope we have enough time for questions, and I hope we're going to have a lively discussion even though it's in the VR conference. So the first paper is from Zamir, Ben-Hur, David Alon, Philip Robinson, and Ravish Mehra from Facebook Reality Labs in Redmond. And the title is, let me see, Localization of Virtual Sounds in Dynamic Listening using Sparse HRTFs. And I could actually participate in one of those experiments, and I'm really happy to see the results. And yes, go on, Zamir, the stage is yours.
Thanks, Johannes. Hi, everyone. Hope you can hear me well. Yeah, this work was done as part of, most of it was done as part of my internship in FRL. Now I'm joined as a postdoc. Yeah, let's start. So the idea is that we as human, using only our 2 ears, we have the ability to hear the spatial sound around us, and specifically to locate the sound sources around us. So if our aim is to reproduce this spatial sound through headphones, we can do it using some binaural reproduction system. And one of the main components of having this high fidelity binaural reproduction is accurate location of the virtual sound. And the main contributor to this is the HRTF component, which provides the main localization cues. So this will be the main focus of this talk. Dynamic binaural reproduction requires high resolution individual HRTFs. But as most of you probably know, it's quite harder to acquire such HRTFs. Here we have, for example, 3 different HRTF measurement systems. As you can see, they required quite special equipment and quite big anechoic room. Although there are some recent development on this side, and there are other systems that allow to have individual HRTF more easily, still it's something that it will be good to have to use just sparse, to have the ability to use sparse HRTF measurement. So now the question is how sparse we can use, and what is the performance, or specifically localization performance, using sparse HRTF. So let me try what. I see the menu on the where I need to change the slide. So yeah, so we can say that we can locate or evaluate our HRTF according to the localization performance that we can get, but we have the trade-off of the availability of the data. So in one end, we will have the true personal HRTF, the best HRTF that we can get, but we don't really have such data. And on the other end, we have the generic HRTF, which is readily available, but the performance is expected to be quite low. And then we can go and ask ourselves what is the performance of using some full measured personal HRTF, and what is the performance of using then sparse HRTF. And as you can see, we have here multiple circles because it depends on how sparse or how many number of measurements, and also what is exactly the representation or the interpolation that we're doing once we have sparse HRTF. But before we can go ahead and evaluate the virtual sound using HRTF, we need to know what is our ground truth. So what is the ground truth localization performance with actual real sound sources. So we first build the ground truth localization experiment with the aim of first validate our experimental setup. So the pointing protocol and our results analysis, and to have a baseline of the subject performance. And we want to be able to do a dynamic localization experiment using this system. So we built the system in this acoustically treated room with a reverberation time of around 0.1 second at 1 kilohertz. In the room, we have 33 loudspeakers. You can see some of them in these red circles. On each loudspeaker, we have a laser pointer on top of the loudspeakers. This is for the training purpose, as I'll explain later. And inside the center of the room, we have this fabric dome. Here you can see it lifted up, but here you have illustration of the dome done with the subject sitting inside. The idea is that the dome obscures the loudspeakers and the subject cannot see the sound sources. Inside this fabric dome, we have the optical camera to track the subject head movement. And using head-mounted laser, the subject points to where he perceives the sound coming from. So the protocol is as follows. The subject is seated at the center of the room, which is also aligned with the center of the dome. Then sound starts playing from one of the loudspeakers, and after the sound is played, the subject needs to point with a head-mounted laser to the direction where he perceives the sounds coming from. And this can be repeated as many times as we like, and for whatever loudspeakers. And for the training purpose, we have visual feedback from the laser pointer on the loudspeaker, and we also have audio feedback from the loudspeaker itself. So this is how the training goes. So the ground truth experiment, we have results of 25 naive subjects. It's important to note that they are naive. It is important to us that this subject never performed such an experiment before. The sound stimulus is a white noise between 200 and 16 kilohertz. And we have two listening conditions. So the first one with a static listener, so short stimulus of 150 milliseconds. And the idea is that this is more for a comparison to previous literature, which most of them have results of a similar static condition. And the other one, dynamic listening, this is the one that was more interesting to us. It's allowed to have some dynamic cues while listening. So we have 3 seconds of stimulus, and we're allowing head rotations of plus minus 15 degrees, both in azimuth and in elevation. So this is to eliminate continuous localization. So you can look and point where the sound is coming from. We don't want to do it. We just want to add some dynamic cues. We start each session with adaptive training with 16 loudspeakers, also out of the 33 loudspeakers that we showed before. And adaptive means that the training is continuous until the subject performance is stable. In the experiment itself, we tested the other 17 directions, time 5 repetitions. So for the results, we looked at the average angular error, and this means so if sound is so this green loudspeaker is playing, and the subject point to somewhere on the sphere, then the spatial angle between these 2 points relative to the center of the head, this is a spatial angle, and we're averaging it across all the repetitions and all directions for each subject. So this is what we see here, split to azimuth and elevation error in degrees. So we see the average results across subject, and the error bars are the standard deviation between subjects. So azimuth error for dynamic, the left one, and static, the right one, and similarly for elevation. So we see that in the azimuth error, we have around 5.5 degrees, and elevation around 7 degrees error. This is quite low, but quite surprisingly, we don't see significant difference between the dynamic and static conditions. We have some higher error in static, but it's definitely not significant. This can be explained by the fact that our experiment is not in a fully free field localization, so it's not in an anechoic room. So maybe some of the room effect also improving the static condition results. So comparing to previous literature, looking at the static results, here we have an example of 4 different studies that performed quite similar static ground truth static condition. So we see azimuth error between 6 and 9 degrees, and elevation error between 8 and 12 degrees. So we can say that our results are quite comparable and even better compared to previous literature. So we can check mark the ground truth experiment. So we have a system that can evaluate accurately the localization performance of 3 loudspeakers. So now we can go ahead and evaluate the virtual sound. So just replacing the actual loudspeaker with headphones, and we can do the same experiment. So first we want to evaluate these 2 corners, so the generic HRTF versus full measure personalized HRTF. For this we measured HRTFs for each subject using our system, which is comprised of an arc-shaped array of 17 loudspeakers, and we're measuring total of 6 number of directions. For the generic HRTF, we measured KEMAR with the same system. For the dynamic, what? Oh, okay. For dynamic listening, we need to do some interpolation. So we are using a simple local linear interpolation using barycentric weight. So the idea is that if we have this ABC HRTF measurements and we want to interpolate to this one here, then we're using these 3 nearest HRTFs and using barycentric weights, which are relative to the triangles areas here, we compute the interpolated HRTF. So it's a simple interpolation that can be performed in real time, and this is what we are doing. At the beginning of each experiment, we are measuring individual headphone EQ using in-ear microphones. You can see here. You also can see in this picture that we're using what we call floating headphones. It was suggested by Romai for localization experiments. So the idea is that we can measure the individual headphone EQ without touching the headphone at the beginning of each session, and also for comparing real and virtual sound sources without affecting the real sound or small effect. So the reproduction system, we have the optical cameras tracking the rigid body on the subject head. We also have the head-mounted laser here on the subject head, and the floating headphones that we can adjust to be directly in front of the ear canal of the subject. In real time, we get the tracking data, and using the HRTF, the measured HRTF, we're using real-time interpolation and incorporating the headphone EQ filter with the dry audio, we get the updated audio, and all this end-to-end latency from head movement to sound update was measured to be less than 40 milliseconds, which is below the threshold is for localization. So the results for the generic HRTF, I don't see the updated slide here. Okay, we have results of the same 25 naive subjects that participated in the ground truth experiment. The stimulus is the same, white noise between 200 and 16 kilohertz. We tested only the dynamic localization. As I said, this is more interesting to us for our applications. We use the same adaptive training procedure as in the ground truth with the actual loudspeakers. So we want to eliminate any learning effect that can be happened when listening to virtual sound with feedback. And we tested 17 directions time for repetitions in the experiment. So these are the results of the generic versus individual, again, azimuth and elevation error in degrees. So we have a yellow bar generic HRTF, in the red one is the individual HRTF, and the blue ones are the ground truth results that I presented before, just for comparison. So we see that the advantage of using individual HRTF, which is more significantly in elevation perception, that we see a big difference between the generic and individual HRTFs. Also in azimuth, we see a difference. And we can also say from here that our results with individual HRTF are comparable to ground truth, although in elevation the result was shown to be statistically significant different, but still the overall result of around 11 degrees further in elevation is quite good. And the difference is that, again, the ground truth is not with in anechoic room, while the individual HRTF here is with HRTF that measured is free field HRTF, and also we have all the errors in the pipeline from the HRTF measurement to the reproduction, interpolation, and the headphone EQ. So all of these components are not perfect, but still we can see that the results are quite promising. So we can say that we can check mark the full measured Pestron HRTF, although it's not as good as ground truth, but still the performance is quite good compared to the generic HRTF, especially in elevation perception. So now we can go ahead and evaluate the sparse personalized HRTF, and we are focusing on the elevation perception. So for the sparse HRTF, we took 4 different subsets out of the full 600 points of the full measured HRTF. So we took a subset of 238 points, 141, 84, and 36 number of points. So in the experiment, we, as I said, we tested only elevation. So we choose 13 directions on the same azimuth arc of plus minus 45 degrees. So we have these 2 arcs with elevations between minus 60 and 60 degree with 10 degree resolution. And we tested it with 3 repetitions. So we have a result of 11 subjects. And so these are the results. Yeah, I forgot to say, we use the same variable, all the different sparse conditions. So what we see here is only the elevation error in degrees. The leftmost bar is for the generic HRTF, the result that I showed before. And then we have all the individual HRTF conditions from the only 36 directions up to 600 directions. The asterisks here suggest represent conditions that are statistically significant difference compared to the full measured HRTF, so compared to the 600 points HRTF. So first we can see from this graph that even with as low as 36 directions, the elevation performance is much better compared to the generic HRTF, so the Kimar HRTF to remind. But also interesting to see that that going down to 84 number of measurement, the result is not significantly different than the full measured HRTF. So these are the 2 interesting results from here. But we need to remember that we are evaluating only elevation perception, so we are not studying any other special attributes or any other artifact that may happen due to the sparse measurement and due to the specific interpolation that we are using. So to summarize, we can say that with only around 100 HRTF measurements, we can get results that are comparable to the full measured HRTF, but the availability of the data is obviously higher. So I presented the localization experiment setup that was validated to accurately showing that it can accurately capturing localization results. We show that the system is flexible. We can do different virtual sound conditions, like different HRTFs, different interpolation method, or different listening conditions. And we showed that the accurate elevation perception can be achieved with only 84 HRTF measurements. So for future work, we would like to evaluate other virtual sound conditions, of course, to study some of the room effects, and to evaluate other perceptual attributes. So maybe not just localization, of course, like externalization or timbre effect, coloration, that may be affected due to the sparse HRTFs. So yeah, thank you very much for listening, and I'll be happy to hear your questions. Thanks.
Yes, really nice talk, Zamir. Thank you. So are there any questions from the audience?
Yes, so at this time, if you want to use the emoji hand raise, we can take your questions now.
Yes, I see. So please raise your
Yes,
hands and ask Zamir questions.
Ben, go ahead and queue up the first question, if you would.
Oh, yeah.
All right, Maximilian, please feel free to ask your question.
Yes, thank you so much for your interesting talk. Very interesting results. But I would be interested about the interpolation method. Could you please go to, I think it's slide 25? Maybe I missed what you said about this, but I was wondering if you have only 100 directions. Is there any very significant influence on the method of interpolation between the HRTFs?
I don't see the slide updates here, but so here I'm using only the barycentric interpolation. In the experiment and in the paper, the full paper, we actually compared the two other different interpolation types using spherical harmonics interpolation. I haven't showed the results here, but the results were surprisingly similar. So with barycentric or with the other spherical harmonics interpolations, the results were very similar. Why the slides are not changing? It's only me, or because I have a backup slide with also results from other experiments. Oh, okay, now it's showing. So yeah, so this is the result. It's not updated. Yeah, never mind. So yeah, we compared also other interpolations, and we showed surprisingly similar results. Is this answering your question?
Oops. Thank you so much. This was really interesting. I didn't expect this.
But yeah. So yeah, here now you can see. So this is the results with using spherical harmonics minimum phase interpolation. They are very similar, and also using spherical harmonics with ear alignment, which is a new method that we developed and published last year. Also, the results are surprisingly similar. Unofficially, subject could tell a different artifact that they could hear while listening. Because different interpolation types, the experiment were performing different sessions, then we can say that there are some more artifact, for example, that related to stability or coloration difference when using spherical harmonics interpolation with a low number of points. But yeah, from the localization results, we can't really see this.
Okay, we have time for one more question.
I might have a question to this, if it's okay.
Yep.
So when you just said you have different artifacts for different interpolation methods, is barycentric then maybe the best for localization, or let's say the elevation cues, and spherical harmonics might be with your ear alignment maybe better for coloration or something? Do you have something like this already, like as you just said, unofficially, or what's the
No,
status?
so yeah. So I don't really have a finalized conclusion that we can share on this. Of course, it's something that we would like to investigate more. Yeah.
All right, thanks. Just a short question. The barycentric, it was on interpolation on the magnitude only, right? It's not the complex.
Yeah, right. The barycentric is using minimum phase representation of the HRTF. Yeah. So we're doing also barycentric on the delays on the ITD. So it's you interpolate separately the delays and the magnitude, and then compose it as a minimum phase function.
All right, thank you. I think we have to go on.
Yes.
The next presenter. Thank you again, Zamir.
Thanks.
My
Thank you
voice is
very
knocked
much.
out. Is it better now, David?
Thanks.
Wait, maybe I'm not amplified. I am. All right, so I'm asking Tim Lübeck to come to stage to make his presentation, please. How do we change the slide decks? Oh. Yes, works for me. So I'm just gonna use you, I think. So yeah, the next presentation is from. Oh, slide disappeared. Okay. The next presentation is from our lab, Audio Group or Institute of Communications Engineering in Cologne of Cologne University of Applied Sciences. Oh yeah, I forgot. Sorry. All right, I'm going to do it again. So the next presentation is from our lab in Audio Group Cologne and in Cologne University of Applied Sciences. The title is Perception of Direct Sound, Early Reflections and Reverberation in Ovalizations of Sparsely Measured Binaural Room Impulse Responses. So yes, Tim, please go on. And yeah.
Just one other point. If we could have the presenters make sure that they are both on air and amplified when they're speaking. You can, of course, mute when you're not speaking, but if you could just check to make sure you're on air, and that way we'll be audible in all the rooms. Thank you. I'm sorry, can we pause for a second? I think we're getting a lot of responses from people that they can't hear you.
Okay.
Dustin? Yeah, he's on air, but we have some issues with the other rooms. Okay, let's see if that works. Thank you.
Okay. Yeah, should I start from the beginning or can I just continue?
I think you should just continue. Yes, thank you.
Okay. Yeah, as I already said, we defined the spatial resolution as the SH order of the dummy head measurement grid. So basically the number of dummy head measurements we need. And then we conducted a listening experiment, an ABX listening experiment, where we try to find exactly the threshold of spatial resolution we need. And then I think you all know the classical binary room pulse model, where we first have the direct sound, which is mainly used for sound source localization. Then we have a number of early reflections, which are more important for the perceived apparent source width, or the timbre, or the spaciousness in general. And then finally we have the reverberation part, and there in theory we don't have any direction dependent component anymore, but we need the reverberation for the perception of room size or the listener envelopment. And so we can assume that for these three parts of the binary room pulse model, we need different spatial resolution for binary reproduction. And then again, as the spatial resolution as the order of the grid order of the dummy head. So we try to answer the question, how many measurements with a dummy head do we need? And yeah, now I will explain you how we calculated the binary room impulse response, which we had tested in the final listening experiment. And we are starting from a dense BIR set. This dense, full circle dense BIR set is defined on a Lebedev grid with 1,202 nodes. And we did not measure this dense BIR set. We calculated it from circle microphone area recordings. Calculated how we calculate BIRs from circle microphone area recordings is studied quite well. And so this is our ground truth, our reference. And then we interpolated sparser BIR sets by interpolation in the circle harmonics domain on the highest order, so the 29th order. And then we resampled those sparser BIR sets, which simulate our sparser measurements. And those BIR sets are defined on Gaussian grids, because Gaussian grids are defined for every spatial order. And so we have 29 order limited BIR sets from order 1, which corresponds to 8 measurement directions, up to 29th order, which corresponds to 1,800 measurement directions. And then to test all these sparse BIR sets in a listening experiment equally, we again resampled those sparse BIR sets to a auralization grid, which was an pure horizontal grid with 360 directions. And this was done again by harmonics domain. And to investigate the direct sounds, the early reflections, and the reverberation part separately, we divided each of these sparser BIR sets after the direct sound, so at 3.5 milliseconds, and then after the mixing time, which was calculated to Abel et al. And then the final listening experiment was done for 4 different rooms to test different reverberation times, and those rooms were measured at the VDR broadcast studios at here in Cologne, and those rooms ranging from reverberation time of 0.25 seconds up to a very large reverberant room with a reverberation time of 1.8 seconds. And then, and as I already said in the introduction, we choose an ABX reinternable to alternative forced choice test. And according to this test design, we always played back 3 stimuli to the participants. Behind the stimuli X, there was always a high resolution reference, so the 29th order BIR set. And then we randomly assigned to either A or B the lower resolution or the hidden reference, so the same high spatial resolution of 29. And then we played back each stimuli one time, and after that the participants had to rate whether A or B was the full resolution, or the stimuli X. And if they could indicate the higher resolution, in the next trial the next higher resolution was presented. If they could not indicate it, at the next trial the next lower resolution was presented. And yeah, this is an one up, one down staircase procedure, which let us converge to the perceptual threshold we want to find. And each condition stops after either 12 reversals. One reversal is one time the participant could distinguish between the lower and higher resolution. The next trial they could not indicate it. This is one reversal, and after 12 of such reversals the condition stops. Or if they could not distinguish between the highest and the lowest resolution, 5 times at the lower bound, so at the first order. Then, as I said, every stimulus was played back one time. During the test, the participants were allowed to move their heads if it helps to distinguish between the resolutions. And so we played back dynamic binaural synthesis, and around about 50 minutes for each experiment, depending on the reverberation time, of course. And yeah, as I said, with a one up, one down staircase procedure, we converge to a threshold, to the perceptual threshold. And in this experiment, we calculated the PSE, so the point of subjective equality. This is exactly the 50 psychosymmetric function, which is a slightly harder criteria as a JND, the just noticeable difference. So the PSE is a point where we basically here no relevant differences anymore. And we calculated this point as the average over the last 9 reversals. Then some more words about the materials. Explained how we calculated the BRIR sets with a lower resolution. Then we splitted each BRIR set after the direct sound and after the mixing time. And then we recombined 3 types of BRIRs by a linear crossfade over 128 samples. And the first type was the DS condition, so the direct sound condition, and this was a BRIR set with completely low resolution. Then the second type was early ref condition, so the early reflection condition. This has high resolution in the direct sound, but order limited resolution in the early reflections and the reverberation. And then the last type, the third type, was the ref condition, the reverberation condition, which has reference, so high resolution in the direct sound, high resolution in the early reflection, but low resolution in the reverberation. And then we tested it for 2 different test signals, so pink noise burst and male German speech, for 2 sound source position, one in the front at 30 degree, one to the right at 270 degree. So in total we had 12 conditions for each room. 3 sparse BRIR components, 2 sound source positions, and 2 test signals. Then here some more setup of the listening experiment. We use a soundscape renderer for dynamic auralization, and Sennheiser HD600 headphones. Then we had 32 participants and divided them into 4 groups with 8 participants each, and each of the groups performed the experiment for 1 room. And here I present you a first overview of the results for each room separately. And on the first view we already can see that, of course, for the direct sound we need all E's than for the later parts of the BRIR. And then we conducted, or we performed a large ANOVA and mixed ANOVA with a between subject factor room and a within subject factor sparse component test signal and sound source position. And here we found that the room was not a significant effect, and so for the following we pooled the data over all rooms. But one interesting note, we found that no participant could hear differences above an order of 23. So we can see that the order of 23 seems to be an upper limit for spatial resolution. And here are the results for the pooled data, and also here we can see that for the direct sound we found higher PSEs than for the later parts of the BIR. For the direct sound we calculated mean values between order 9 to 13, and for the early reflections and the reverberation orders about 3 to 4. And then on the pooled data we performed a measured ANOVA with a within subject factor sparse component, test signal and sound source position. And of course we found that the sparse component was a main effect. We see for the direct sound we have higher peaks, early reflections and the reverberation. Then we found that the test signal was a, and yeah, we can see that the noise signal is a more critical test signal than the speech test signal, and a reason for that could be that the timbre or the spectrum of the BIRs is more important to hear the differences than, for example, the spaciousness, and there the noise test signal is more critical for the spectrum. And see that the dependency on the test signal seems to vanish BIR, and this is supported by the ANOVA. We found an interaction effect of sparse component and test signal, and the same applies for the sparse component and source position. So for the later parts of the BIR, the sound source position seems to be not that important anymore. And yeah, now I will play back some static stimuli of the small broadcast studio. This is a room with a reverberation time of 1 second, and I will present you a noise stimuli at the right side, so at 270 degree, and then I will present you the highest resolution, then the lowest resolution, and then successively the thresholds we found in the listening experiment. So for the direct sound an order of 10, and for the reverberation and the early reflection. And yeah, I don't know which level the video will be played back, so yeah, maybe keep a finger on the volume button, and you will hear the noise signal. So I heard a lot of artifacts. What about you?
Yes, there were sadly artifacts which we did
Okay.
testing.
Yeah. Then in the testing we thought about restarting the space when there are artifacts. I don't know if it's necessary or what we do now. Or should I try playback again? Then I will play back again, and maybe you can raise your hand if there are still artifacts. Okay. I thought that you might said something. What should I do?
Yeah, I was just suggesting that you advance the slide. Unfortunately, we have that terrible default YouTube's page of recommendations. But if you do want to replay something, you can go back a few slides and then forward and come back to the same audio slide.
I will try it. And then I will play back. So no, I can't hear anything.
And now please advance the slide just one forward. There we go. And I heard that fine myself. I don't know if other people did. Looks like we got some good
Okay.
responses. Yep. Great. So do you want to proceed forward, Tim?
Yeah. So I can explain what we can here. So in the direct. Yeah. Sorry.
Good.
Yeah. So in the direct sound, we can clearly hear that we have an shift in direction, but we can also hear that for the early reflection and the reverberation, even on the third order, we can't hear any differences to the full resolution, and that's basically what the okay, and that would correspond to 30 points on a Gaussian grid. And then we found that no participant could hear differences above an order of 23. And yeah, we can use these findings for, yeah, of course, we can lower the memory capacity of. If we store the direct sound on the high resolution and the early reflections on the third order grids, that would be lower the memory capacity enormously on AR or VR devices. The same could be applied to the rendering. If we find an algorithm to render the direct sound and the later part of the BIR separately, this could also save a lot of performance. And last but not least, this could also, we can think about lowering the memory. If we find a nice algorithm for upsampling the direct sound, which is possible because it's just in plane wave, or even replace the direct sound with an HRTF measured in dry conditions, and measure our 30 points to resolve the early reflections and the reverberations, it would be completely enough and would lower the measurement effort enormously. And then at the future work, in the beginning I said that we defined the spatial order, the spatial resolution as the order of the dummy head measurement grid, but we can also think about defining the order of the ambisonics representation. For example, if we capture the sound wheel with a spherical microphone array, we just have a limited number of microphones. We just can resolve a limited ambisonics order. And then it would be interesting if we have the same artifacts or even the same thresholds. But this is in future work. Yeah, thank you very much. That's everything from my side. Do you have questions?
Yes, thank you very much, Tim. And sorry for jumping on stage. So are there any questions? Raise hand. I don't feel like asking questions here.
Remember, you can raise your hand using the hand raise emoji.
I
Feel
see.
free to raise
Isaac,
your
how
hand
do
at
I?
any time.
I see
Isaac.
you raise your hand. Oh yeah.
Yeah, it looks
You
like
do?
we do have a question. Ben, go ahead and
Hello,
call on that
can you
one.
hear me?
Yeah,
Yeah.
we can hear you, Isaac.
Nice. Thank you, team, for the presentation. I thought it was super interesting. So I have two questions. The first is, do you expect the results to be much different with an individual HRTF? And the second question is, do you think, did you expect the early reflections and the late reverb to have that different threshold? And in that case, do you think if you use even a smaller room with stronger early reflections, you will see a higher threshold for that part of the BRIR?
Yeah, to the first question, if the results would be different with individual HRTFs, I think the results would be different with individual HRTFs, but we can also think about defining the Yeah, that's a very good question. As I said, in this experiment, we just tested the horizontal plane, and as we saw in the talk before, individual HRTFs are more relevant for the perception of elevation. So yeah, I don't know, but I don't think that the differences would be that much different, especially because our high-resolution reference also was in calculated BRI set from circle microphone area recording, and there we have the similar reference, so I don't think that the jump between the lower resolution and the high resolution would be much different if we have individual HRTF, but we should test it, I don't know. And the second question was the difference between early reflections and reverberation in other rooms, or what exactly was the second question?
So he asked higher thresholds maybe in small rooms which have a higher density of reflections or stronger early reflections.
Yeah, I think we tested the very dry room, 0.25 seconds. I think this is even very, very dry. So yeah, I just can guess. I don't think that the results would be different that much. But just a guess. We see in the ANOVA of all data where we had the room as a factor, that the room is not a significant effect, but I just can guess. So I think the results would be the same in dry rooms, in very, very dry rooms.
All right, thank you very much. I think we have time for one more question when I look at the schedule. But
Yes, we have
if
time.
there are no, yeah. So if there are any more questions, please ask.
You gotta raise your hand if you want to ask a question. You can do that with the emoji hand raise.
Okay. Then I would, yeah, applaud and try on with the presentations. Thank you, Tim.
Thanks.
Hi. I think I'm seeing the wrong set of slides. No problem. Yaks. Yeah, that's correct.
Dustin? What paper number are you loading? Ah, there we go.
This looks good.
Now I see it.
Looks good. Yeah. Thank you.
And the presenters, if you could just check one more time to make sure you're both on air and amplified in the host
Yes.
tools.
Can you hear me well? I think I'm amplified and on air.
Yeah, and we might want to just check briefly with the other rooms. Dustin,
Right.
is there any word on the other rooms hearing okay? Yep.
So you just give me a go.
Yes. Okay, I think that was a thumbs up. So yeah, we can go ahead and start.
Okay. So the next paper is from Sebastian Nagel, Daniel Haupt, and Peter Jax from the Institute of Communication Systems of the RWTH in Aachen. The title of the paper is Coherence Adaptive Binaural Q Adaptation, and it's about binauralization, let's say, of static scenes, or dynamic binauralization of static scenes. So yes, please go ahead, Sebastian, and yes, thank you.
Yes, thank you for the kind introduction. So, yeah, as you just said, the title of my paper and the name of the algorithm I'm presenting is Coherence Adaptive Binaural Q Adaptation. But before I start, maybe I would like to give some motivation. So we're all experiencing AltSpace VR, the spatial audio teleconferencing, and it's quite beneficial to have spatial audio in teleconferencing. And the way it works here is that we have the individual recordings of the speakers and also the knowledge of the speaker locations. And so we can use binaural rendering. And if you are lucky, you're using an HMD to listen to this, then you have even head tracking, which improves binaural rendering, makes it more natural, and gives us improved localization and reduced front-back confusion and in-head localization. But let's now consider maybe a slightly different application. Let's say the pandemic is over and finally people can meet again, but they also want to use spatial audio for their teleconferencing, and we have this scenario that's shown here where we have 3 people meeting in a physical room and a 4th person who would like to...
I'm sorry to interrupt. Sebastian?
Yes.
Yeah, I'm sorry.
Sure.
That we got a thumbs up and now it's a thumbs down. Apparently
Okay.
the live stream also is not seeing the correct slides. So let's go ahead and do a space reset, and then we can see about the other rooms. Which room is this live streamer in? Can you tell me, Dustin? Is he in this room?
That
I'm
is a bit
not sure. I'm working on it.
slide.
Okay. I can't make that up, but I'm going to just reset the space first of all then.
Okay, so I hope everybody can still hear me. Okay.
Which kind of slides do you see now, Sebastian?
I see my slide number 3.
Okay, now I see also other slides only from Bishop Gupta. Okay, I just see in live stream it works. For me, I have old slides now, other slides.
Yeah, I can go back. Can you see me changing the slides?
Yeah, why don't you go back to the beginning and
Sure.
give a restart.
Okay, so let's try again. Sorry about that. No problem. So yes, as a motivation, I was just saying that we're experiencing the benefits of spatial audio for teleconferencing, and it works in AltSpace because we can use binaural rendering, because we have individually recorded speakers and also known speaker locations. And if you're lucky and you're using an head-mounted device, then you can even have head tracking, which is also quite beneficial. And So I would like to point your attention now to a slightly different scenario where we have maybe after the pandemic is over, people are meeting again physically, but they still would like to have spatial audio conferencing. And so here we have 3 people in at a conference table and a 4th person who is participating in this physical meeting remotely. So one way to achieve this or to realize spatial audio in such a scenario would be to simply use a binaural recording device, such as maybe an artificial head. And if you take the 2 microphone signals from such a device and transmit them to the headphones, then you get pretty easily a quite realistic spatial image of the scene for this remote participant. And now the question is, how could we realize head tracking for this person who is listening to this binaural recording? And so that's the goal of the binaural cue adaptation algorithm that I'm going to present in the remainder of the talk. So we can add head tracking to the playback of conventional 2-channel binaural recordings. And the idea is shown here in this sketch. So in the recording scenario, we have some artificial head or some recording device with 2 microphones, and there's maybe a sound source at a certain angle that's called phi original here. And then we take the ear signals, the microphone signals, transmit them. And now if we have a listener who's looking into a slightly different direction, maybe looking slightly to the left compared to the original device, then in order for him to perceive the sound source in the same spot, we need to shift the sound source a bit to the right. So we need to rotate the scene contrary to the listener head rotations. And to do that, we use the binaural cue adaptation algorithm. We measure the head rotation angle with a head tracker, and we adapt the binaural cues in real time by applying a filter. And before I go into details of how this algorithm works, I would like to show you a short demo. So in this demo, you can see a recording of me using a real-time demonstrator that we have at the Institute. And the demonstrator shows you a video that is recorded in this setup that you see here. We have an artificial head and a GoPro camera mounted on top of the artificial head. And if you watch the video, maybe try to pay attention to how the sound sources, the sound source directions change with the listener head movements. Okay, so I hope most of you could see the video okay and also hear the sound binaurally and hear the effects. I think I saw some sad smiley faces during the talk, so maybe if you would like to see the demo and you didn't have a chance, just talk to me later and I can send you the YouTube link and you can have a look. I think that's maybe the easiest way. Okay, so coming back to the algorithm, this is a block diagram of how the architecture of the algorithm looks like. So we have the binaural signal going in at the left, and then we take this binaural signal and transform it to the time frequency domain. And then we do an analysis where we try to estimate the direction in every time frequency bin with from these signals using an HRTF model. And we use this estimated source direction and the information that's provided by our head tracker to determine how we need to modify the binaural cues in order to rotate the scene as is required for the application. And so we get an output signal that has been rotated and we transform this back to the time domain and we can play it back with the headphones. And the architecture as is shown here was already published by us in a previous paper that's cited down here. And in this new paper presented here, we're extending this architecture with a better signal model that can takes into account incoherent components in the signal. So we enhance the signal model and we can get better estimates of the binaural cues, phase and level differences, and also an estimate of the coherent to incoherent power ratio. And I will show you later how we use all this to obtain a better modification filter for our signal. So let me start by going through this block diagram. First, we'll have a look at the head-related transfer functions. So we have HRTFs for different directions. And here we use a spherical head model. So this means we're using an analytic model, not actually measured HRTFs here. And we can define intraoral level differences and intraoral phase differences for the different directions by taking the relative transfer function between these HRTFs and then the magnitude as the level difference and the phase as the phase difference. And so the limitations that come with this kind of modeling need to be mentioned here. One is the cone of confusion. So because the head is modeled as a sphere, we don't have a pinna, and obviously we need pinna cues for elevation perception. So since we don't have pinna cues in this model, we cannot do that. And also the binaural cues are not do not necessarily contain pinna cues in general. So to do something like this, we would need a more sophisticated algorithm. And instead, we're here assuming that the sources are located on the frontal horizontal plane. And yeah, we think that this limitation actually is quite applicable to many real-life scenarios, such as teleconferencing or concert recording, as you saw in the demo. So let's now have a look at the signal model. Here we have the binaurally recorded signals that we have available, and we assume that these can be interpreted as a coherent component, which is a source signal with the respective HRTFs, and an incoherent component, which is called N here. And using this signal model, we can define binaural cues in the signal, similar to the binaural cues from the HRTF database before, by taking the relative transfer function between the coherent components and then again the magnitude and the phase of that. And this should give us an idea of where the sound source is. And again, there are some assumptions here. One assumption is that there's only one coherent component per time frequency bin, which is a simplification that we need to make because then we have one relative transfer function between these coherent components corresponding to the sound source direction. But it also many sparse signals in the real world are sparse. Many source signals in the real world are sparse, so this assumption might make sense. And the other assumption is that we have no direction dependence of the incoherent components. This is of course a simplification if the incoherent components model things such as reverberation, but it makes things easier for us in the next steps. So now let's have a look at how we can use this signal model, because obviously the difficulty is that we have only these signals X available, but we have no separate estimates of the coherent and incoherent components. So we need to do something else to treat them differently, and that is we can estimate the auto and cross power spectral densities of the input signals. And then from this and some assumptions that we make on the model, we can actually derive binaural Q estimates, so the relative transfer function between the coherent components, and also a quantity that will become important later on, and that's the ratio of the coherent component power. This gives us an idea of if the time frequency bin that we're seeing is dominated by, say, reverberation or maybe by direct sound. So this, so much about the signal model. Let's now have a look at how the direction estimation works. So here we have as input the ILD and IPDs that we estimated from the signal, so the ratio of the coherent components, and also the ILDs and IPDs from our HRTF models for the different directions. And the idea is to identify the best match for these observed binaural cues to identify the most likely direction. And to do that, we can use the algorithm by Zuhur, Jan, and Martin that does a minimum mean square error optimization and effectively yields this equation shown here, where we get the best matching direction in terms of ILD and IPD in our signal compared with the HRTF model. So now we have some rough idea of where our source might be in a given time frequency bin, and also we know the head direction or the head rotation of the listener, and we can worry about how we can modify the binaural cues. So the goal is now to change the source direction by modifying the binaural cues, and the binaural cues are in this model the ratios of the coherent components. So from the previous step, we know the ratio of the coherent components in the input signal corresponds to the ratio of the HRTFs for the original angle, and we can use this original angle to calculate the desired angle with the head tracking information. And then we can again have a look at the HRTF model and find out what are the HRTFs or the binaural cues for the desired location, and that's the relative transfer function between the coherent component that we would like in our output signal. And then the goal of modifying the binaural cues is to change this ratio in the output signal. So the idea is we apply a filter to the coherent component that will change the ratio between the different channels to what is desired, and the equation for this filter is given here. So the filter is given in the frequency domain, so these are complex coefficients, but essentially it's a linear filter that's applied to the coherent components actually. And before I go into detail about what the difficulty is there, let me just point out something very quickly, and that's if the listener is looking in the frontal direction, then we have no modification of the signal. So the system is transparent in this case, and I like to think of it as like a minimally invasive algorithm that doesn't distort or change the signal if there's no need, because the listener is looking in the same direction as the recording device. Then we can just take the binaural signal as we record it, and we don't need to do anything to it. So this, as I said, this filter gives us a way to modify the coherent component. But now we have this problem that we can that I'm showing here. So we have the desired output signal, where we have a filtered version of the coherent component, and the incoherent component, things such as reverberation, we would like to use. We would like to remain unchanged, because in the model these are independent of the direction where the user is looking. And the actual output signal that we can obtain with a linear filter, however, so here the linear filtering coefficient is called Wi, and if we apply this filter to the input signal X, then we apply it to both the coherent and the incoherent components. And since unfortunately we don't have separate estimates of the coherent and incoherent components, all we can do is actually the second case where we apply it to the entire signal, and this can cause the following problem. So previously in the first publication, we just applied this filter to the entire signal, and this means that we do modify the coherent component as is desired, and we modify the direction, but we also distort the incoherent component. And this could mean that, for example, if we had moved the source to the left, then the reverberation would also seem panned to the left. And we want to have a better approach. So we say here that we want to optimize the filter that we apply to the signal so that the energy of the error signal is minimized. And the error signal is the difference between the output signal and the signal that we can get from this filter. And the result, if you do this minimization, is quite interesting and is shown here. So it's basically the Q modification filter that we want to apply to the coherent component, but scaled with the ratio of the coherent component power in the total power that we get from our signal model and the power spectral densities. And what this means is maybe best illustrated if we look at some corner cases. So if the coherent component dominates, then this coherent power ratio is close to 1. And this means that we effectively apply the Q modification filter G to X and modify the direction. And if we have a segment of the signal where the incoherent component dominates, then this factor turns close to 0. So this means that we leave the signal unchanged basically. So the filter coefficients become 1. And this means that instead of modifying the direction, we preserve the incoherent component. So basically the algorithm can now switch between two modes, either modifying the direction and modifying the entire signal, or preserving the incoherent component and not modifying the signal. So modifying the signal less often. And just to point this out again, if the user is looking to the front, then we get GI equal to 1 and then also WI equal to 1. So the system is still transparent and not doing anything if it doesn't need to. So before I go into some illustration of how this algorithm works, just one short remark, and that is in the paper there's also a bit more sophisticated filtering structure derived. So what I showed you is we have a separate filter for every channel, and there's no crosstalk, so to say, between the input channels to obtain the output channels, and it's also possible to obtain a filter structure as shown in the right, which we call combined filtering in the paper. So here for the right output channel, for example, you would not only have a filter that gives you like a modification of the right input channel, but also a contribution from the left input channel to the right output channel. And yeah, we can show with some results that this also improves the results. So yeah, here you can see an illustration again of these of how this algorithm can switch between two different modes. So there are two quantities shown here. The first one in the top is the output ILD error. So this is an error that we can make in modifying the coherent component. And in the bottom it shows an incoherent power error. So this is a quantity that measures how much we distort the incoherent component. And of course we would like to have both these errors to be equal to or to be as low as possible. And what you can also see on the x-axis, we have the coherent to incoherent power ratio of the input signal. And the original algorithm, as previously published, it always behaves independently of the coherent to incoherent ratio. So it always does the same thing, always tries to apply the Q modification filter. And thus the output ILD error to the coherent component is always 0, but the distortion to the incoherent component is always there. And the new algorithm is different. It can switch between the corner cases as shown before. So the corner case to the right is where we have a perfect modification of the coherent component, but distortion of the incoherent component, and to the left is the opposite, where we preserve the incoherent component, but we make some error in the coherent component. And actually that's a behavior that we want, because if we are in the left, then the coherent component is so much, the incoherent component is actually dominating. And so an error in not modifying the coherent component is probably not audible, and the same to the right. So in these corner cases, the algorithm does just what we want. And in the middle, there's at least a smooth transition. So this curve is actually just the result of the optimization that I showed you earlier, and it's not necessarily maybe the best in a sense of auditory criteria, but at least there's some smooth transition. And just for completeness, there's also, you can do the same results with the combined filtering and get even better results in these metrics. And maybe something for clarification. So the input coherent to incoherent ratio on the x-axis is not actually stationary, but it's changing all the time in the signal. So maybe if you have a speech onset, then you are somewhere on the right and you need to modify the direction. And if you then have later something that's maybe reverberation or ambient noise, then you want to preserve that, and then you're on the left. So the algorithm is constantly tracking this coherent to incoherent ratio, and the operation mode is constantly moving on the x-axis. Okay, so before I finish, I have some a bit more academic audio examples for you where you can actually hear the difference between the different algorithms.
As an audio example, I have a speech source in the front mixed with white noise that I'm trying to move using the algorithms to the left. I will play the input signal first.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
There is a reference signal where the source has been simulated at the left. So this is what the algorithm is trying to achieve.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
The original algorithm will move the source, but will also move the incoherent component. So the noise should be amplified in the left and attenuated in the right channel, which sounds different than the reference.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
The coherence adaptive algorithm should perform much better in this regard.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
If you listen closely to the incoherent noise in the right channel, you may notice some fluctuations with the speech activity.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
This problem can be solved with the combined optimization of the filters and using the cross paths.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Just for comparison, I will play again the reference signal and the output of the combined algorithm.
To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so. To administer medicine to animals is frequently a very difficult matter, and yet sometimes it's necessary to do so.
Okay, I hope most of you could hear the audio examples. I'm sorry about the echo. Obviously, should have muted myself. So again, if you would like me to show you these videos, just talk to me afterwards, and I will be happy to. So maybe just as a short summary, I presented an algorithm, binaural cue adaptation, that makes binaural recordings interactive, and you can adapt static binaural recordings to head movements of the listener. And in this paper presented at this conference, we're adding a signal model with incoherent components, which allows us to do the coherence adaptive modification, and we think that this improves the subjective quality for signals that contain incoherent components. So thank you for your attention, and I'll be happy to answer any questions.
Yes, thank you very much, Sebastian. Really interesting. Are there any questions in the audience?
If
So
you have any
please
questions,
raise your
just
hand.
use the hand raise emoji.
Yeah, I see one hand raise here. The first panel.
Hi, excellent talk, excellent paper. I was curious, so taking specifically binaural recordings, could this algorithm possibly be used to convert previous ORTF, XY, other stereo recordings, such as previous classical recordings and stuff like that, and then convert it into what could be used in a VR situation?
Yes, that's a very interesting question. So I think maybe the first thing to say is that this algorithm, of course, works with existing binaural recordings very well. So in fact, the demo that I showed you was a recording that we did before we even had this algorithm. So you can take any binaural recording from YouTube and get somewhat immersive experience. And the applicability to other recordings, of course, depends maybe a bit on adapting the signal model, because maybe there's in a stereo signal, I would expect there to be maybe less interaural level differences. So maybe the HRTF model does not really fit this use case well, but I think it can probably be adapted to quite a lot of different applications maybe. I hope this answers your question. I don't see the...
Carl,
Yeah, seems okay.
you could ask your question now.
Could you please say a little bit about how this compares to the state-of-the-art or early attempts to do this? Because when I remember right, I got demos showing similar ideas.
Okay. Actually, I don't know of any previous attempts at solving this problem.
Could you repeat
unless
the
they
question?
use...
Could you repeat the question, please? So we can all hear it.
Okay, I think the question was how this compares to previous attempts at solving this problem. And unfortunately, to the best of my knowledge, there are not any attempts to solve this for purely binaural recordings. So of course there are many methods to do binaural rendering if you know the source signals, and also there are methods to do recording of scenes spatially using like ambisonics or motion track binaural, where you have always additional microphones additionally to the two binaural microphones. So if you know anything that works with only two microphones, then I would be very interested to hear about this. But I'm not aware of any of such algorithms.
So, are there any more questions?
Hello. Can you hear me?
Yes?
Yeah, I just have a quick question. I might have missed some parts, but I'm wondering the HRTF model you're using, does that depend on the head microphones that's used for recording the binaural sound?
Yes and no. So the question was, does the HRTF model depend on the head microphones used for recording the sound? And yes, I expect the results to be maybe more accurate if the HRTF model resembles the HRTFs of the device used for the recording. But oh, now I hear an echo of myself. Yeah. Yeah, but for some simplification, the model that we're using in the algorithm, as I showed it to you, the spherical head model actually is very generic, so it doesn't even resemble any real-life HRTFs. But it still works quite well, and it's actually a bit more robust because it's yeah, it has some advantages, and it can be calculated analytically. And so yeah, it's a bit generic.
I would have maybe one last quick question. You already talked about ambisonics, and where do you see the advantage of your method? Okay, there are like, let's say, two microphones, and maybe you have first order ambisonics, where you don't have the drawbacks of like the cone of confusion, where you cannot.
Johannes, could you amplify your voice, Johannes?
Oh, I'm again missing this. I thought it's turned on. Let me see. Yeah, it's turned off again. Sorry. So I'm going to ask again. Where do you see the advantage over like the first order instruction, where you, on the other hand, don't have the drawbacks of not being able to resolve ILD and ITD on the cone of confusion, meaning you can have sources also in the back, for example, of your listener?
Yeah, thank you for this question. So I think it's actually a bit of a different use case, because if you have an ambisonics microphone, then of course you can do fourth order ambisonics. Maybe one advantage of the approach here would be that if you are looking to the front, then you have a binaural signal. So this might actually be a bit better than a first order ambisonics recording that's binaurally rendered. So this might be one application, but I think the more interesting application is actually where you have only the binaural signal. So for example, if you only transmit the stereo signal, it's maybe easier to transmit over existing channels as an ambisonic signal. Or if you have maybe some spatial audio rendering engine where you get a pre-rendered signal and you want to add head tracking to this, and you have no access to the underlying ambisonics representation or something else, then I think this algorithm might also give you kind of the best you can get in this situation, if you for some reason cannot get any better in the layers below, so to say.
Okay, so it's also thought as kind of an upmixing algorithm for...
Yes.
Okay, cool. Thanks.
Mm-hmm.
All right, if there are no more questions, and I think we are also out of time, and we need to continue with Thomas.
Okay, then thank you again.
Hello.
All right, we don't see your slides yet, at least not me.
Dustin, are you loading the slides? Dustin, are you loading the slide deck? Okay.
Okay, how is the sound? Can you hear me clearly?
You sound good. We just need to get your deck loaded. I think it's paper number 14.
Yes, that's correct.
Okay. Dustin, I'm going to go ahead and load this deck. If you can hear me, I'll just go ahead and put it in. Okay, I'm hoping that some people can see Tomas's slide deck. Let me go to the front and see if there are how many. Why don't we see how many sad faces are there still?
I think the response is positive from my perspective.
It looks like a pretty good response.
Nice.
Overall. Now, Dustin, if you can hold for just a minute, Tomas, I want to check on the other mirrored spaces and see. I am getting some responses.
Sad faces too,
Dustin, can you hear me?
All right.
Okay. All right. Yeah, we can. I think we can afford to do that for just a few minutes. He's going to reset the other rooms so that we have at least a little bit better chance of everybody seeing the slides. I think during the last presentation, I don't know what our percentage was. It's very hard to see, but I think it wasn't great. It might have been 80% of the people could see them, but in any case, it might just help to do the reset in each of the other rooms and see if we can get that working. And we'll also, of course, check the
Now I see the slide deck from Sebastian again.
Yeah, I see it as well. So it works for me.
I'm gonna re-enter again. Worked for me earlier too. Let's see.
Okay, what about now? Okay, no problem. So, hi everyone, I'm Tomasz Rudzki, and I'm a PhD student at Audio Lab at the University of York. And in this talk, I'd like to present my research on the use of eye tracking for auditory localization testing. And more specifically, we're going to talk about the measurement of perceived lateral angle when simple binaural stimuli are applied to our ears. So first, I will present some background information. Then we're going to move on to experimental design. And then I will talk about the proposed workflow for eye tracking data analysis in such tests. And then we'll briefly go through results and conclusions. So the auditory localization tests are used in different fields, and there are different use cases for such tests. Starting from spatial perception research. And another use case is the evaluation of spatial audio rendering schemes, as well as HRTF sets and signal processing techniques. And some newer use cases include running such tests for evaluation of coding algorithms for immersive media streaming. Please excuse me, we are resetting the space, I see. Oops. Yeah, that's okay. That's okay. I just need to get my slides open, and it will be just a second. Let me see. Let's go to another one. And there's a number of established methods for running such tests, starting with simple stuff like displaying 2D interface on the screen, and we ask participants to point where's the location of the sound source, to more sophisticated ones. Some of them require adjustment of the visual or auditory pointer using and head pointing methods. But all of these methods, they have some drawbacks, some limitations. They all require different degrees of cognitive load. I see some sad faces. I hope we can fix it. And they all require some sort of motoric response. Let's say the user needs to use their hand or orient their head towards the sound source. And usually, in such tests, the training has a positive impact in terms of improving the performance of the participant. And another group of tests, subgroup, is the tests run using the VR or augmented reality headset. So these tests, they are quite convenient to prepare. We can provide controlled visual environment. And because the headsets have their motion tracking built in, we don't need to use external tracking systems. And sometimes we can even test using the delivery platform. For example, in immersive streaming, we can test using 360 video playback, or we can test auditory performance, localization performance in VR gaming. And some of the new headsets, they have built-in eye tracking capabilities. And here comes the question, can we make use of the eye tracking to leverage, to improve the testing schemes? So from previous research, we know that eye tracking in localization tests works for real sound sources like loudspeakers. And the general conclusion is that auditory evoked eye movements are accurate and precise. However, we have obvious limitation of the human field of view, so we cannot test all directions. And with video-based eye trackers, there is a significant performance decrease at the peripheral gaze directions. So let's go to another question. Can we use eye tracking in binaural-based evaluations, where we do not have real sound sources, but we use some sort of virtual acoustics or filtering? Well, if we do not provide the proper spectral cues, if we do not have the proper virtual acoustics, then we end up with very often with the sound which is not externalized and it appears inside our head. So we decided to test from the ground and introduce only basic binaural cues like level and time difference. However, in such case, the listeners, they perceive sound as being inside their head. And we call it lateralization. And this is the shift of the sound image inside the head on the interaural axis. So is there a relation between lateralization and direction of the sound source if the sound source would be presented outside of our head? Well, and there is, as long as we provide visual reference of the distance to the participant. And once the participant has like a distant reference, they can, the relationship is quite simple, and it's that trigonometric identity. So we have designed an experiment using the augmented reality headset, which will provide that reference, distance reference. We did a playback of binaural stimuli, and we decided to measure the perceived lateral angle using two methods. First is the eye tracking method, and the other one as a reference, the pointer adjustment method, where we have to adjust the visual pointer using the hand controller of the Magic Leap headset to match the position of the perceived sound source. So our test equipment and software consisted of the Magic Leap headset running Unity 3D app that provided the 3D environment. On another machine, we ran this Salty framework, which is like a custom software for running listening tests. And this software is available on GitHub if someone is interested in using it. It is developed in our lab. And we did use Sennheiser HD650 headphones to playback our stimuli. So the test control and data collection was done by that C++ software called Salty. This is the 3D environment that we use in the experiment. The spherical grid is like the head of the participant is placed inside of this grid. On the right, you can see the participant's view. The red dot is the visual target, which we use in the experiment, and I'll explain it in a second. And the green dot is the pointer which we use for pointer adjustment method. The radius of the sphere is 1.2 meter. So we ask our participants to focus their gaze somewhere on the grid in the distance of 1.2 meter from the center of their head. The auditory stimuli that we've used in this experiment consisted of pink noise with 5 milliseconds fade in and fade out envelopes. And we had two groups of stimuli, one with introduced time difference and another one with introduced level difference. So we divided this, we have, so this stimuli was ranging from minus 267 to 267 microseconds for time difference, divided in 17 equal steps. Similarly, 17 equal steps for ILD from minus 4 dB to 4 dB. We've also used high pass and low pass filtering to avoid conflicting cues because the time and level based localization works best in these frequency regions. So we pay attention for these two bands not to overlap. So, and these, I mean, with the current eye tracking techniques, we need to conduct calibration. And we decided to use two-step calibration. The first one is the native calibration, which is done before each experimental session, and it's provided by Magic Leap. And another step is it's built-in visual targets into the sequence during the experiment. So based on the data gathered in response to visual targets, we can conduct offline calibration in the post-processing of data. So that's why the experiment consists of these alternating visual and auditory stimuli groups. To look more in detail on the experiment, we had 5 repetitions of 34 auditory targets, 17 for ITD and the same 17 for ILD. And the duration of single trial was 1,250 milliseconds, and the presentation was continuous. So we do not require any feedback from the participant other than just following the direction of the sound with their gaze. So the overall test duration was 5 minutes 40 seconds. And it is slightly different in the pointer adjustment method because we have to wait for the participant to confirm the response. So they've used the trigger to confirm the response. And of course, in such case, the time of the experiment depends on the individual participant. And unfortunately, in this research, I was the only one who took part because of the limitations of the current pandemic. I could not conduct any tests with other listeners. So I've repeated the whole procedure 3 times, and that's the preliminary data that we will try to analyze. So now let's go to the eye tracking data analysis workflow. What you see now, it's the raw gaze data sampled at 60 Hertz across the time of the whole experiment. So we can see that the gaze was focused along the horizontal plane, and there was not much eyes activity in the vertical space, which was exactly what we wanted, what we tested. We have limited the experiment to horizontal plane. If we look at the graph representing the azimuthal data and the time series data in the first 60 seconds of the experiment, we can see like a groups of black dots, and these dots, they represent fixations, which is the response of the eye when actually it's when the eye is focused on the target, and we want to localize these fixations, and we want to quantify them for further processing. If we look more closely, and here is the graph of representing time series data of across single experimental trial, but overlaid of 17 trials. First, on the left, we see fixation corresponding to the target from the previous trial. Then we see the gaze shift, and after that, we see that in general the eyes are fixated on the next target. So the gaze shift is called saccade or saccadic eye movement. And for our analysis, we take the last fixation from the trial and we take it as a response. Another graph shows the eye activity during the trial based on the angular velocity. And we can see the sharp peak, which is the response to the visual stimuli. And the response to auditory stimuli is slightly different. It's more smeared in time. And why is that? Because the response to visual stimuli, it's a single saccade. And we have usually like one main saccade and then occurring one or two corrective saccades. That's why these graphs shows that activity. And before we go into results, I just want to remind what's the difference between accuracy and precision, because it is always good to get the grip of these two terms. So by accuracy, we mean the mean distance of responses from the target location, and by precision, we mean the spread of the responses, basically. So let's go to the results. What we can see here, it's the single responses from each trial using both methods. The red one is the pointer adjustment method. So we have a response as a lateral angle in the function of time difference applied to our stimuli. We can see some correlation, but still it's kind of a blurred image of anything happening. So let's look at the means of these experiments. And in this graph, you can see that the mean response for eye tracking method, same for the pointer, is quite similar. And this means we can say that these two methods are accurate in reference to each other. But we cannot say that the overall accuracy of the experiment is good, because it's like a psychophysical relationship which is not known. Another graph shows the data collected with level difference, and it's similar situation. However, we see some disparity between pointer and eye tracking method. I think it's because these experiments were taken on different days, and I believe that my individual sensitivity or difference in sensitivity between two ears might have been impacted by some external factors, like, I don't know, allergy, let's say. So that's why the level difference is different between these two methods. But I'm not going to go into details on that. Another thing is the precision that we have analyzed from this data. So we can see that the precision of eye movements towards the visual target is quite high. The variable localization error is low, under 1 degree. And the error for eye tracking based method and pointer adjust method is comparable, and it is like between 3 and 4 degrees. Sometimes this variable error, which corresponds to precision, is known as RMS error, depending on which research we are looking at. And another thing that's our attempt to compare the physiological measurement, which is the eye tracking based measurement and pointer adjustment, with physical data obtained through HRTF measurements. So we have extracted the ITT values from 3 HRTF sets, like 2 standard ones, like K100 KIMAR head, and individual HRTF set. We can see that this data, there is a strong correlation between perceptually measured and physically measured data, which is optimistic, I would say. There is some difference, but still we would need to have more participants to make such conclusions that it means anything. And similarly for ILD, we have some agreement, this agreement of the slope, and some difference in the offset of these curves, which might be there might be different reasons for that, and we would need just more measurements to make conclusions. But however, let's summarize. Eye tracking might be a time-efficient and robust localization testing method. I think it will require less cognitive load, and that's why I need to run more tests with more people to state this. Maybe it's like a less engaging method and just easier to work with. The achieved accuracy and precision is similar to the visual pointer adjustment method, and it turns out that it is feasible to use consumer AR/VR devices which have eye tracking capabilities for running such tests. And it's just this increases the possibility of running localization tests in times like now, where we do not have access to our laboratories. Our future work will, of course, involve repeating the test with a high number of participants. We want to use HRTF-based localization testing to evaluate how the spectral cues. Can we use eye tracking for tests involving perception in the elevation using spectral cues from HRTFs? And like the broader research topic, which I find interesting, is the perceptually driven optimization of frontal sound source rendering using data collected during tests like eye tracking, for example, because it seems that using such tests we can collect lots of data in a short amount of time, and maybe based on that we can tweak some parameters of binaural rendering. So thank you for listening. If you have any questions, feel free to write me an email or contact on LinkedIn, and feel free to ask questions now. Thank you.
All right, thank you very much, Tomasz. And sorry that I couldn't introduce you. I had to re-enter space. So yeah, are there any questions? Please raise your hands.
Remember to click the raise hand icon if you have any questions.
There's one.
Patrick, go ahead.
Yeah, so one of the key benefits of this system was obviously that you can assess a lot of localizations in a short amount of time. What sort of gain are you talking in comparison to the controller pointer?
Yes. To answer this, in my case, because I was the only one who did the experiment, it takes around 3 to 4 seconds to respond with the controller and to adjust the visual pointer. Where if we look at this time characteristics of the eye response, we see that around 60 milliseconds since the beginning of the trial, basically the eyes are at their destination or focused on the target. But on the other hand, it's probably not feasible to run tests with a speed of less than 1 second and require participants to turn their eyes with such high rate. So I would say maybe it's 50% increase, but it needs further testing. And of course, it does not need the motoric response of using the controller. And I find this test much less demanding in terms of focus, and that has to be maintained during the test. And I'm looking forward to run more tests to see if other people will agree with this.
Any more questions? I might have one then. Just checking if I'm amplified. So is there any work done already in terms of eye movements for sound sources in the vertical or in the median plane, as you said? To the horizontal domain, and yeah, are there also saccades in this direction?
Yes. Although yes, and based on the previous research by John van Opstal and some other great minds, these saccades they behave pretty similar to the horizontal plane. However, it has not been researched extensively in terms of HRTF-based specialization. Like these tests were done mostly with, or maybe exclusively with real sound sources. So the application of such tests to HRTF-related problems has not been yet researched, based on my knowledge at least.
All right, thanks.
Thank you.
Okay, so if there are no more questions, I would this first session, paper session of this year's AVAR conference, and thank you all for those for great talks and nice papers, and thanks the audience for being here and for participating. And see you in half an hour in the next session.
Thank you, Johannes, for also being the session chair.
You're welcome.
All right, we'll resume here in about half an hour. I just unmuted everyone, so everyone is free to chat, and that's fine.